Yes, so this video is about something called reaction stoichiometry, and stoichiometry to me is essentially dimensional analysis specifically with chemical reactions, but we'll get a definition a little bit further down. But before we get to the chemistry, I want to talk about this idea of making pancakes, and we're going to use this analogy to introduce this idea of stoichiometry. So if we were making pancakes, if you look here, right, we know that we need a recipe. We can't just, wing it and hope we understand what, or think we know what pancakes are made out of or anything that we're trying to make. So we know that we need mixed milk and eggs, and that leads to our pancakes, but it's not enough to just know what you need. You need to know how much of each. So this that I'm boxing right now, I would relate to a balanced chemical reaction, right? That's the analogy here. And we know that anytime we write a reaction, it has to be balanced. And we can't just hope that a whole box of pancake mix takes 1 cup of milk, right? We need to read the recipe to figure out what we need. So we have our balanced chemical reaction. And if we look at the question we have here, it says if we have a fridge full of milk and eggs, right? So we have essentially an unlimited amount of milk and eggs, but we look and we only have 2.5 cups of mix. The question that we have is how many pancakes can we make? And when we're looking at here, and notice it says show your work with dimensional analysis. That's the key here. And I know you can do this without dimensional analysis right now, and you can probably do it with fractions and ratios, but we are going to practice dimensional analysis so that when we get into the chemistry end of this and the real stoichiometry, we understand how our dimensional analysis plays into the stoichiometry. Okay, so in general, right, we need to make sure that we have enough of each ingredient. So in this case, we know that we have essentially unlimited milk and eggs, right? We have excess amount of these. It's the cups of mix that is really going to limit the amount of pancakes we can make. So if I have 2.5 cups of mix, remember dimensional analysis is starting with what you have and converting it to what you want. And this balanced chemical reaction, or our recipe, right, our recipe, well, that one shouldn't be in quotes, the balanced chemical reaction should be, this provides us the ratios of ingredients and the product, right, or our finished amount. And it's through this ratio that we are going to be able to answer this question, because if I look at the recipe, I need 1 cup of mix, which then will give me 8 pancakes, assuming that I have enough of everything else, and based on the question we do. So I can say for every 1 cup of mix, we get 8 pancakes. And so this will work out to 20 pancakes, and that's our answer. Now, if we had not enough milk or mix to get to 20 pancakes, then we'd have to do some more math to figure that out, and we'll actually see that with our next example. But in this case, we had enough of everything else. So our amount of pancakes that we can make is 20. And again, we're showing with dimensional analysis with that idea of canceling out the unit we have to get to the unit that we want. And this came from our balanced chemical reaction, or our recipe, okay? Now, as I was just saying, like, imagine we have this case where we don't have a fridge full of milk and eggs, but we look and we see in the pantry we have 6.5 cups of mix, but we only have 5 cups of milk and 3 eggs, right? We go through our pantry and our refrigerator, and that's what we have. So the question is still, how many pancakes can we make? But in this instance, the difference is the first question we had 1 number, right? 1 amount of ingredient. Now we have 3 separate numbers of ingredient. Okay. So if we want to figure out how many pancakes we can make, well, we need to figure out how many pancakes we can make with each amount of ingredient, and whichever one gives us the least amount is the what we're going to call the limiting reactant. It's the one that limits you, and even though I would have enough, say, mix and milk to make a certain amount of pancakes, well, I only have a certain amount of eggs, or, you know, depending on where our math takes us. So I'm going to scoot over here, and we're going to have 6 cups of mix. We're going to have 5 cups of milk, and we have 3 eggs. And again, we're going to treat each of these individual ingredients separately, as if, let's imagine we had enough of everything else and we had 6.5 cups of milk, or of mix, how many pancakes we would make, and we're going to do that for all of them. And again, we're still relying on this one simple balanced chemical reaction. Okay, so we know that for every 1 cup of mix, we can make 8 pancakes. And then it was 3/4 of a cup of milk, 3/4 cup milk. We get 8 pancakes. Right, all I'm doing is looking at the recipe and comparing the two. So before we had mix and milk and pancakes, now we have mix and milk. Right, that's the one I just used. And then the last one we're going to do is the pancakes and eggs. Right, so 1 egg for 8 pancakes. Right, and why is it always 8 pancakes? Because I'm looking at this recipe that we have, and the recipe is written for our simplest ratios, right? 1 3/4 1 for 8 pancakes. So that's why that's why in this case it's always going to be 8 pancakes. So if I do this first one, 6.5 cups of mix, if we had enough of everything else and 6.5 cups of mix was the amount that was holding us back, we can make a total of 52 pancakes. That's a lot that we can make. And I'm going to do the same thing for, times 8 divided by 0.75. I'm going to do the same thing for the milk. If we had enough of everything else and 5 cups of milk was the thing that limited us, we can make 53 1/3 pancakes. It's slightly more than the mix allows, but if we come over here, we see for the eggs, we can, if we have enough of everything else and we only had 3 eggs to use, then we can only make 24 pancakes. So now when we're assessing this problem, if we had this amount of ingredients, how many could we make? Well, right, in order to make 52 pancakes, I need a certain amount of eggs, and I only have 3 eggs. So this calculation we just did allows us to realize that the 3 eggs limits the recipe, or we can think of limits the reaction. I don't have enough of this in order to fulfill the recipe. So our answer has to come from the limiting factor, right? The thing that holds us back. So our answer for how many pancakes we can make is 24, because, and you don't have to write this, but I'm writing it out here so you don't have to keep, right, so, well, you can't, but I can. I don't want to keep sliding back there. So 24 pancakes because 3 eggs is limiting factor. Okay, I'm going to call it the limiting reactant when we talk about stoichiometry, but it's the thing that holds us back. And along with these types of questions where we're figuring out we have multiple ingredients and we're figuring out how much of the product we can make, there's this secondary question that we can ask, which is how much of each ingredient is left over. So the easiest one here is eggs, right? So in order to make 24 pancakes, we need to use 3 eggs, right? So if I think of the eggs, we started with 3, and then we used 3. So there are 0 eggs left over. 0. And that's going to be true of every limiting factor, right? If we had more eggs, we would have been able to make more pancakes and so on, right? So whatever the limiting factor is, you're going to have 0 left over. But it's still this idea of how much you started with subtracted from how much you used is how much you have left over, right? I'm going to remove these what are those things called? Commas. And we started with 3, and we're going to subtract how many used, which was 3, and that's going to equal 0. And this premise is going to hold true for your mix and your milk as well. How much we started with minus how much we used is going to be how much we have left over. So mix, right? We started with 6.5 cups. So our question is how many cups of mix did we use? And the way that we're going to do this is with another dimensional analysis, but we need to know what to start with, okay? So the thing that we tend to start with is the amount of pancakes that we actually made, right? So I made 24 pancakes. So in order to figure out how much mix we used, we can work backwards, right? I made 24 pancakes. I know the ratio is for every 8 pancakes, I need 1 cup of mix, and therefore we used 3 cups of mix, right? Or, that's one thing we can do, or we can start with the amount of eggs we used, right? So I used 3 eggs. And if I come back over here, this recipe allows me to go from any ingredient or product to another one. So I don't always have to go from reactant to product. I could say, well, if I use 3 eggs, or for every egg I use, how much mix do I use, right? It's a 1-to-1 ratio. So I can come back here and say for every 1 egg, I use 1 cup of mix. Eggs cancel out, as it should, and we still get the same answer. So it doesn't matter which way you go. And 3 cups of mix, I think it's important to underline the fact that this was how much we used based on what our recipe was. So I can either think about I made 24 pancakes, therefore I used 3 cups of mix, or I used 3 eggs and the ratio is 1-to-1 eggs to mix, so I also used 3 cups of mix. So then we could come over here, we used 3 cups, so therefore we have 3.5 cups mix left over. And we would go through the same process with the milk. You can either use the pancakes, you can use the cups of mix, or the eggs. It does not matter what you use. You're going to get the same answer because you're using the same balanced chemical equation, the balanced recipe. So I'll come over here. I'm going to stick with the pancakes. But again, you're going to get the same answer no matter what you use, right? So there's 3/4 of a cup of milk used for every 8 pancakes made. And if we get this, 24 divided by 8 times 0.75. So we use 2.25 cups of milk. And we can say for the milk, we started with 5 cups. We used 2.25. Oopsies. So we have 2.75, 2 3/4 cups of milk left over. Okay, so there's quite a few different questions that we can ask when we're doing these problems, but they all are relying on this balanced chemical reaction, the ratio of the ingredients to the products, or the reactants to the products. And everything that we did involved that ratio, okay? So if we want to get some formal notes on reaction stoichiometry, here's the definition of it. It's the quantitative assessment of chemicals in a reaction, so that means we're using numbers. And because all of the problem that we did is coming from the balanced chemical reaction, what that provides us with is a mole-to-mole ratio, right? We can say moles of pancakes to moles of cups of mix, but we're gonna see our example down below. But in order to do stoichiometry, you need a mole-to-mole ratio. If you do not have a mole-to-mole ratio, then you're not doing stoichiometry. You need to use the balanced chemical equation. So remember that saying we have, when in doubt, mole it out. This is key here. If you don't turn what you have to moles, then you can't use a mole-to-mole ratio, and if you don't use a mole-to-mole ratio, you're not doing stoichiometry. So again, it's coming from a balanced chemical equation. Never assume a chemical reaction is balanced. You can tell me if it's balanced, and you also know how to balance the reaction. So make sure that every reaction you look at is balanced. So here we have nitrogen reacting with hydrogen to form NH3, which is ammonia. This is a balanced reaction, but again, you can tell me that it's balanced. And another way to read a chemical reaction is with the coefficients that you have, right? No coefficient, we assume 1. So it means for every 1 mole of nitrogen, we need 3 moles of hydrogen to react, and we're going to make 2 moles of ammonia. So we can't always say that the amount of moles on one side is equal to the amount of moles on the other side, right? Because I have 4 total moles on the left side and 2 total moles on the right side. So it's not simple arithmetic. You have to balance the chemical equation, making sure that you have the correct number on each side. So the recipe as written gives us 2 moles of ammonia, but we know that we can adjust recipes, and it's based on the ratios. So our question that we have, how many moles of nitrogen are needed to produce 1 mole of ammonia? And since that value, we don't see 1 mole of ammonia here, we can always be thinking about dimensional analysis. And if you have a balanced chemical reaction, then you have your mole-to-mole ratio. And as long as that substances as long as those 2 substances are related in the reaction, then you can write that conversion factor that compares the 2 of them. So I'm interested in moles of nitrogen. I have moles of ammonia, and now where would I put in this ratio comes directly from the balanced equation. Okay, and I literally just pluck the numbers from the reaction, right? For every 1 mole of nitrogen that I react, I get 2 moles of NH3. So in order to produce just 1 mole of NH3, I just have to half the reaction, right? I need 0.5 moles of N2. Okay. And it really is, right, if you know how many moles that you have or how many moles that you're reacting, you can do a mole-to-mole ratio to quickly figure out how much of the other substance you want or need. And what we were doing before is this idea when we were here, when you're given multiple numbers of ingredients or of reactants, that is this idea of limiting reactant. Okay, it's when you are given 2 or more amounts of reactants and you need to figure out which one limits the amount of product that can be made. And we did just that, right? We came over here and we figured out which one gives us the least amount of product. And when you start your dimensional analysis with that amount, we're saying if all of that 6.5 cups of mix are used, how many pancakes can I make? When all of the 5 cups of milk are used, how many pancakes can we make when all of the 3 eggs are used? Now, I'm not always going to use all of it because I am beholden to the ratio in our recipe. Now, we know in cooking that you can obviously mix up your ratios and not get the desired product. In chemistry, it is more stringent. Like if you do not have enough, the reaction will not go. I know that we can cook and create the product that is not good on the end, but in chemistry, the ratios do hold true. So even though I calculated 52 pancakes, well, I couldn't make that many pancakes because of the limiting factor of the 3 eggs. Okay, so whenever you start with your dimensional analysis with in stoichiometry, you're assuming that you used all of those or you made all of those pancakes, or all of that amount. So that's why it's super important to figure out what your limiting reactant is first. So if the eggs are called the limiting reactant, everything else is called the excess reactant. So the milk and the mix would be called excess. And we saw that we can calculate how much we have left over simply by figuring out how much we started with and subtracting how much we used. And to note, if you are given only one amount of reactant, then it's assumed that you have excess of the other. So looking at the question we just had, the how many moles of nitrogen are needed to produce 1 mole of NH3, that's assuming we have enough hydrogen, and you can say that, right? 0.2 moles of nitrogen, assuming we have enough hydrogen. But if you're not given the amount of hydrogen, you can just assume that you have excess hydrogen or more than enough hydrogen. Okay, the next video that I put out will have some examples for using this stoichiometry with limiting reactants.